Hello and welcome back. So we were looking at the Butler-Volmer equation through different reaction kinetics, and we considered one electrode, hydrogen electrode in this case, and then we formulated the equations for forward current and the reverse current, and we are trying to find out the net current, which is the difference between the forward and reverse currents. So during this course of equations, we also came across something called as exchange current, which is basically a representation of the current that is flowing through the circuit or across this electrode when there is no net current flowing in the external circuit. So when the forward and reverse current equate each other, we get something called as exchange current. So let us take these equations ahead and formulate our equation for the net current. So let us write, if you remember from our equation 1, from equation 1, so I can write I equals N F A K naught C, this the concentration of the species at the interface at a given time, e to the power 1 minus alpha and f eta by RT. We also have a second term for the oxidized species, or minus alpha and f eta by RT. So if I rearrange these terms, we will know that the term on outside the bracket is nothing but your exchange current I naught, and I can write the same expression again, CR 0 T by C. C is nothing but the bulk concentration of this species, and we have assumed them to be same because at T, when there is no net current flowing in the circuit, we have both of these species concentration, we can assume them to be equal because they are bulk in concentration, 1 minus alpha and f eta by RT minus 0 T by C to the power minus alpha and f eta by RT. Now this expression is called as very famous Butler equation, and this is in general form, right. So what does it say? It says that if you look at this expression, it says that if the net current produced through the electrochemical reaction, this I, it increases exponentially with this overpotential that we have, and that is, let me write that down. So Butler-Volmer equation, that is BV equation, states that the current produced by an electrochemical reaction increases exponentially with the overpotential. So this line is important, increases exponentially with the overpotential. So let me explain this. So in other words, what is our eta? Eta is basically, eta is E naught minus E. So it is basically difference in the reversible cell potential and the operating potential. So let us say we are talking about the fuel cell, this is our IV curve, this is our E naught, and this is, let us say, E1, which is our first operating potential, then this is, let us say, E2 and E3. So as this difference, this is potential, as this E naught minus E, which is E naught minus E1 or E naught minus E2 or E naught minus E3, this difference increases, the current that we can draw from the cell will also increase. So, same thing can also be explained or rather illustrated for the electrolyzer. So, here your eta is negative, as we can see this E naught minus E again. So, operating potentials are higher than the reversible cell potentials. Let me say this is E3, E2 and E1, this is our E naught. So, here eta will be negative in this, let me write this as well. So, this will be negative in case of electrolyzer or electrolysis, and this eta will be positive for fuel cell. So, as our eta increases, so even if you take the magnitude of this overpotential, it says that as your magnitude of eta increases, the current that can be supplied in case of electrolyzer can also will also increase. So, I can write this in case of fuel cell, since it is E1 is it should be smaller than E2, smaller, sorry, I should write like this. So, E1 is greater than E2, greater than E3. So, your eta 1 is smaller than eta 2, smaller than eta 3, because the difference is between E naught and E. So, this is in case of fuel cell. How do we do it with the electrolysis? So, your E1 is smaller than E2, so it is smaller than E3. So, your eta 1 is basically eta 2 and eta 3. So, they are also smaller than eta 2 and eta 3. So, eta 3, or I can write it specifically for fuel cell, eta 1 is E naught minus E1, eta 2 is equal to E naught minus eta 2, and eta 3 is E naught minus eta 3. Here in case of electrolysis, it is eta 1 is E naught minus E1, eta 2 is E naught minus E2, and eta 3 is E naught minus E3. So, as we can see, E3 is the farthest operating point than compared to the E naught. So, eta 3 is larger than the other two cases. How it comes with the chemical barrier? So, I can draw that. So, this is our equilibrium reaction or equilibrium status. This is the state 1 and this state 2. So, this is just like this. So, if I have two containers filled with water, they are connected with the pipe. So, if I want to have water flowing between these two containers 1 and 2, I need to bring in some imbalance in the system. So, imbalance can be in the form of tuning the elevation levels of either one of the containers. So, if I bring more elevation difference, let me draw it with the other line. So, if I do it like this is my second case where I have brought the small difference, and another third case can be like this. If I differ that elevation difference by a large amount, then the large water will flow from A to B. So, this is nothing but the eta that we are talking about. So, this is the equilibrium condition. The second case, this is our eta, as I can say, this is in the form of eta 1. So, eta 1 will be look something like this. So, this is our eta 1, wherein we are lowering the reaction barrier for the forward reaction. So, your eta, that is the reaction barrier for the forward reaction, will be smaller compared to that of the reverse reaction, and hence the forward current will flow. And how is the case with the second case? This will be eta 2. So, eta 2 will be like this. So, this is our eta 2. and so on and so forth. So, as your eta increases, the more current will flow in the respective direction. Here in this case, the forward current will flow because we are favoring the forward reaction. So, this is our forward reaction and this is the reverse reaction at a given electrode, at a particular electrode. So, this is our equilibrium. So, let me also simplify what Butler-Volmer equation states. It states that Butler equation states that if we want more electricity or I would say current. So, I am going to specifically write for fuel cell. So, we must pay the price in terms of the loss in the potential. Which is nothing but overpotential. So, you have to underline this, you have to pay the price in terms of loss in the overpotential, and that is what we have just seen. If your eta increases, the net current flowing in the across the electrode will also increase. So, let us move on. So, again let us go with the equilibrium. So, at equilibrium we know that the species concentration at the interface at a given time to the bulk concentration is, they both are same. So, I can write it for the reduced species or the oxidized species, and that ratio is 1. So, how does it look like in case of Butler-Volmer equation? This Butler-Volmer equation reduces to this form, e to the power 1 minus alpha n f eta by RT minus e to the power minus alpha n f eta by RT. The ratio has been nullified. So, it is 1, and if I want to now plot this with respect to the different currents, how does it look like? Let me use that equation one more time. So, it is I equals I naught e to the power 1 minus alpha n f eta by RT minus RT. So, how does that equation look like? So, let us draw it. Okay. So, these are the overpotentials, positive overpotentials. This is the anodic current and cathodic current. So, anodic current means the forward current and the cathodic current means the reverse current at a particular electrode. So, how does it look like for a different electrocatalyst? How does an electrocatalyst, in other words, play an important role in catalyzing these reactions? Let us see that. So, let me draw this. If I am using a, let us say, a good catalyst, should pass through the center. So, let us say this is our platinum, and here in this case will be iridium, because negative overpotential means it is an electrolyzer. So, this is the electrolyzer domain, this is EL and this side is your FC. The first quadrant represents the fuel cell reaction, whereas the third quadrant represents the electrolysis reaction. And what happens if I use an inferior catalyst, say nickel, it will look like this. So, what does it imply? It implies that this is nickel. So, if I take the example of or the case of fuel cell, I can see that if I want to draw a similar current, I have to so this is the current that let us say I am drawing. So, this will be the our potential that is invested if I am using platinum as an electrocatalyst, and this will be the over potential invested or used if I am using a nickel as a catalyst. So, for the same current, this current I am basically losing a very less potential for the good catalyst, whereas for a similar current to be drawn from the fuel cell, if I am using an inferior catalyst, I have to sacrifice more potential loss, and that is what this Butler-Volmer equation talks about. The same thing also happens here. This is, let us say, this current is what I am expecting. So, this is your eta iridium, and this, let us take this cobalt. So, this is my eta cobalt, and this is IC, the IC that we are interested at. So, the similar things can also be explained in case of electrolyzer. For a better catalyst, we are investing in terms of lower overpotential to get the same cathodic current IC, whereas if we use the inferior catalyst such as cobalt compared to iridium, so we have to invest more potential to basically carry out those reactions to achieve that rate of reaction. So, let me write that. So, with better catalyst, we can get more anodic current in fuel cell mode. That implies your eta is positive, and same thing is also applicable in case of electrolyzer. So, with a better catalyst, we can get better or more cathodic current. In the electrolysis mode, eta will be negative in that case, right. Let us move on. So, we have seen how electrocatalyst plays a vital role in reducing the overpotential. Let us have a quick look at how the transfer coefficient alpha also plays an important role. So, let me draw that. Okay. So, again the same axis we have used, it is plus eta, positive eta, this is negative eta, which means this is your electrolyzer quadrant, third quadrant, and the first quadrant is the fuel cell quadrant. So, as we know, alpha, which is the transfer coefficient, alpha is a transfer coefficient which has a value from 0 to 1. Typical value is around 0.5, typically around 0.5. So, let us take the example of equilibrium condition. So, we have this is our equilibrium condition, wherein the net reaction is, or the net current flowing in the circuit is 0. Now, let us tune this alpha, see what happens. So, I am going to use purple color. So, my alpha, let us say, is 0.25. So, 0.25 means it will be shifted to like this. So, this is my alpha equals 0.25. So, again it has to pass through the center of the axis. So, this is my alpha equals 0.25. What happens if I am using alpha as 0.75? If I am using 0.75, it will be like this. This is alpha as 0.75. So, if my alpha is 0.75, it will be like this. This is alpha is 0.75. So, alpha is 0.75, alpha is 0.25. So, of course, the alpha when it is 0.5, it will be at the center. So, this is alpha equals 0.5. So, if I have a quick look at the reaction or the equation rather. So, we know I equals I naught and alpha, let me take an example of alpha is 0.25. So, when alpha is 0.25 for a fuel cell, let us say if I want to forward or I want to basically favor this forward reaction, this is our forward reaction, that is H2 giving 2H plus 2 electrons. So, if you want to favor the fuel cell reaction, I have chosen alpha to be 0.25. So, if we recollect the expression for the Butler-Volmer equation, it is e to the power 1 minus alpha. So, 1 minus alpha stands for plus 0.75 eta and NF eta by RT minus e to the power minus 0.25 NF eta by RT. So, if you look at this expression, we can see that I can write this same expression as e to the power 0.75 NF eta by RT minus this is e to the power minus 0.25, I can bring it to denominator e to the power 0.25 NF eta by RT. So, if you can see that if my eta is increasing, this term will increase, this term will increase and this term will decrease, right. So, in other words, my forward reaction will be favored if my alpha is 0.25 and if the alpha is let us say 0.75, in that case the reverse reaction can be favored. So, this is the example or rather significance of transfer coefficient. So, we can tune this transfer coefficient in case of electrocatalyst that we are synthesizing and we can favor one particular reaction or whether it is a fuel cell reaction or an electrolyzer reaction. So, I can write this lower for a fuel cell, basically lower is alpha, better will be anodic current, right. So, this is the case of fuel cell. So, having understood the significance of electrocatalyst and the transfer coefficient, we will now look at the Tafel equations in the upcoming classes. Thank you.